This is Algebraic Reasoning, Chapter 1.1, Exercises 1 through 10. For questions 1 through 4, write an explicit rule that describes the number of items used to construct the pattern in terms of the number n. So I'm probably going to do just one of these four, and just to give some direction on this. So basically you have four images, and the first image on the left, image number 1, we'll call that, has 4 squares. The second one has 6 squares. The third one has 8 squares, and the fourth one has 10 squares. And one way to handle this, probably the easiest way I know to do it, is to create a table, and our input value is going to be n, and says number of items, and so I'm going to use the variable I for items. So number of items depends on what the value of n is, the block number. So I'm going to put down here 1, 2, 3, 4. So if we plug in 1 for n, we get 4 items. If we plug in 2, we get 6 items, or 6 squares. Plug in 3, we get 8 squares. We plug in 4, we get 10 squares. So what we have are, we can kind of analyze by putting little brackets on each side, just kind of seeing what happens. And we should notice on the left side that we are increasing by 1 every time as we go from 1 to 4. On the right side, 4 plus 1 equals 6, well, that's going to be plus 2. And likewise from 6 to 8 plus 2. And finally from 8 to 10 plus 2, so plus 2 every time. So what this tells us is n is equal to 2i. But we have to get a starting point. And to get a starting point, if we can see where n is equal to 0, that will give us what our starting point is. Well, you notice that we went up 2 every time as we went from 4 to 6, from 6 to 8, and 8 to 10. So we know if we go up plus 2, following the pattern to get from 0 to 1 on the left side, what does this number here have to be? The number here has to be 2. So our explicit rule is going to be 2 plus 2i, because 2 is where we started out. And this is kind of like, you can rewrite this. We can say n is equal to 2i plus 2. We can write it that way also. But that's just kind of a logical approach of looking at it. In terms of equivalency, if we were looking in algebra equation here, we would say this one here, this 2 would be the slope, or the coefficient, and this other 2 over here will be our y-intercept. And this one right here is an arithmetic sequence. Arithmetic means constant finite differences. I think of these remaining 3, I think two of those remaining 3 are linear, but just go through that same process like I worked out number 1 and see how that goes for you. Next, Segway Tours in Corpus Christi charges $12 an hour to rent a Segway, an additional fee of $4 for the required helmet. David can create an arithmetic sequence that shows the cost of renting a Segway. And here we have a pattern, and we can do this similar to the way we did problem 1 a bit ago. Our first term is 16, second is 28, third term is 40, and our fourth term is 52. So if we come to the right side, we can say okay, it will be, we input the number of hours, and we'll call that H, I guess. And then what will be the cost? Okay, cost equals C. So if we go 1 hour, we'll get 16. 2 hours will cost us $28. 3 hours will cost us $40. And finally, 4 hours will cost us $52. So we notice we're going up by 1 on this left side. On the right, we're going to determine what these things are going up by. See if it is a common difference. So to find that, if we take 28 minus 16, we get 12. And we could go ahead and create a function. That would be one way to do this. Another way to do this would be just to continue our table. Okay, 5, 6. So we know if we add another 12 to 52, we're going to get 64. And then to get to 6 hours, we're going to have to add another 12. So 64 plus 12, 76. So we will say, how much will it cost? It will cost $76. Okay, that's number 5. 6 is a quite related problem to this. Write a function rule, and you can figure that out, I hope. Next, Roger dropped a ball from a height of 1,000 centimeters. The height of the ball is 80% of the previous height after each bounce of the ball. Roger can create a geometric sequence that shows the height of the ball at the end of each bounce. What was the height of the ball after the 5th bounce? So you can just kind of look at it the way we did this other one. So if we just go ahead and take this right here. Okay, say bounce number, and then we have height. Okay, first bounce is 800 centimeters. Second bounce is 640 centimeters. Third bounce is 512 centimeters. And fourth bounce is 409.6 centimeters. And again, on the left, we have our increments are going up by 1 each time. But on the right, let's see what's happening here. If we take 800 minus 640, we're going down 160. If we go to the next increment, 640 minus 512, that's going to be minus 128. Okay, so we definitely do not have a common difference. The problem tells us what the situation is if we read this carefully. And what it says is the height of the ball is 80% of the previous height after each bounce. So 80% decimalized equals times 0.8. So we're going to instead multiply by 0.8, and we're going to get in the direction we want to head. So we find at the end of each bounce, after 5 bounces, well, it's going to be one more bounce. And so we're going to multiply by 0.8 yet again. But we can just check this as we go along. And for this, I'm not planning to use an on-screen calculator, but have a off-screen calculator explaining what's going on here. So really, if these things check out correctly, the only thing we should have to do is take that 409.6 and multiply it by 0.8 and get our correct answer. It's taking my calculator a bit of time to turn on one of these TI Inspire CX calculators. Okay, there it is. Come to life. It's making me put everything new on this. Okay, there we go. Fresh from the factory. All right. So we will say, let's just assume that we got it right here. I'm going to put 600 times 0.8 just to be sure that we have the right pattern. Yeah, 640. Okay, 640 times 0.8. We get 512 times 0.8. We get 409.6 times 0.8. We get 327.68. So 327. So our answer would be 327.68 centimeters. And this one here, write a function for that. I'll leave that to the reader to do that. Here we have problems 9 and 10. We have Clayton has a savings account with $11 he got from his grandmother each month after the initial deposit. He adds $15 to the account. Clayton could create an arithmetic sequence that shows the balance of his savings account at the end of each month after he deposits funds in the same account. And so we have kind of like after each month after initial deposit, he adds $15. So this will be that first month after he opens, and he'll have that amount, second month, third month. So we can create a table similar to what we did in problem 1. We have our month number, and we have our dollars. I'll say D for dollars. And so after 1 month, we will have, Clayton will have $26. After 2 months, you have $41. After 3 months, you'll have $56. Okay, how much will he have after 12 months? Well, we can just keep on going like we did earlier, but I make a suggestion here that instead of just adding, what are we adding every time? What was Clayton adding? Plus 15. Okay, plus 15. What if instead of just adding 15 every time, we created instead a function rule? Now it gives you a hint. Clayton has a savings account with $11 in it, so if we go to 0 times 0, we start out with $11, or Clayton did, and then to get from 0 to 1, he had to add 15 to get to that first month amount of $26. And so we have a formula here, or can have one, where our amount is equal to 15 times the month number plus the starting amount of 11. So in this case, for the 12th month, we have 15 times our month number, which is 12, plus 11. And should be able to do that without a calculator pretty easily. Be 144 plus 36 plus 11. I'll just put this in the calculator. Okay, it looks like I have $191. Just spell it out. And problem 10 is a part of it. It's the function rule. Well, actually, we actually have the function rule, I believe, from what we did earlier. Anyway, that's going to be this video segment. Good luck, and thanks for viewing.